Yes, here we are. It's the physics video lecture. Physics 2A, video lecture 34. We're back to fluid mechanics now. This is chapter 9, fluid mechanics, and we're starting a new topic, fluid dynamics, so fluids in motion. So let's differentiate here for a minute. So if we're talking about fluids, we had fluid statics. So fluid statics, our main result was Archimedes' principle. Okay? And the various things that we can do with the buoyancy force. But now we're going to talk about fluids in motion, which is dynamics. And there's a whole range of interesting phenomena there. In fact, weather phenomena are the most dramatic example of fluid phenomena, and they're very difficult to calculate. So we're going to have to start with easier stuff. Dynamics of fluids in motion. And the first thing, we have to draw a distinction between different types of fluid flows. So we have a flow when a fluid is moving, and it can be either laminar or turbulent. Laminar is a smooth flow, and turbulent is a chaotic flow. So laminar versus turbulent. And a good way to get a visualization of this is if you have a candle burning. Okay, there's a candle, and there's the flame. Put some color in our flame. Okay, maybe a little red. But anyway, you've got that flame, and you snuff the candle out, and what's left is some smoke that's rising. And what you'll find is that the smoke rises very smoothly. And what that smoke is showing you is that while the candle was burning, there was a fluid flow, okay? There was a flow of the air, but at a sufficient distance above the candle, maybe just a foot or so, it's going to dissipate and become turbulent. Okay? So this would be the laminar section, and up here where it's all chaotic and dissipated would be the turbulent section. So this would be laminar, and this here would be the turbulent part, and you get that when you snuff out a candle. Good example. Or someone has a cigarette on an ashtray, and then there's some smoke rising from it. It'll start out laminar, and then it'll become turbulent as well. Okay, so when we talk about fluid flows, ideal fluid flows, the kind that we can work with in this class, we're talking first of all about laminar flows. So they're going to be laminar, and the second thing, they are going to be incompressible. And the third point we're going to make is that they will be frictionless. Frictionless, so there's no internal friction, no loss of energy due to friction, and in terms of fluids we say there's no viscosity. Then when you've studied this for a while, you add viscosity and friction and things get a lot more difficult. So these are our ideal fluid flows that we're going to study, and yeah, that's the good background. Okay, so next we're going to consider first a flow through a constriction. So everybody's had water flowing through a hose, and you constrict the end and it shoots out, or you run water through a hose in a nozzle. So the first example is the flow through a constriction. And I'll draw a pipe that narrows and then it widens again. So there we have a perfect constriction here. And the idea is that the flow is going to be faster if you've done this before. If you cut it off here at the end and it were a nozzle, it would be coming out faster. So it's going to be faster in the constriction and slower in the wider part. But we can be quantitative with that now. So what we'll do is we'll take a cross-sectional area like that, and that would be area sub 1, and we'll take a cross-sectional area there, and we'll call that area sub 2. Okay, so we kind of anticipate that the speed is smaller through area sub 1 and faster through area sub 2, so we'll have a V sub 1 and a V sub 2. And we're going to assume this incompressibility here, and mass is certainly conserved. In other words, as much water flows into the constriction as flows out of the constriction. Okay, that's what we mean when we say mass is conserved. So delta M over delta T in area sub 1 here is delta M over delta T in area sub 2. Okay, same amount of mass per time flowing in here, flowing out there. Okay, so now let's see what that means. For the mass, and the delta T is the same, so for the mass on the one side we have density times volume over time through 1 is density times volume over time through the sub 2 there, okay. Now, I just said, but I erased it, but I just had up here that the densities are the same because it's incompressible, okay. Incompressible means the density is the same. The volume is A times delta X. Now, why don't I go ahead and put a delta T here like I had before, okay. So I have A times delta X, that gives me a volume over delta T, and that's A sub 1, delta X sub 1, delta T, and that's going to be A sub 2, delta X sub 2, delta T. Okay. So yeah, I canceled the, because density is constant, so I did that. And now what do I have here? I have A sub 1, B sub 1 is equal to A sub 2, B sub 2. So something like that had to be expected, and it's a pretty simple relation. So the cross-sectional area times the speed of the flow is conserved. So over here on the left, area is larger, the speed is smaller. Over here on the right, the area is smaller, the speed is greater. Okay. So this is called the continuity equation. Continuity equation. Let me write that so it's legible. Important equation here. Okay, so that's the continuity equation. That's the first equation of fluid dynamics. And there's really a couple of interesting examples. I'm not sure if this one's in the book, but this is something everybody has seen. If you have a faucet, that water can run out of, not with an aerator, okay? So let's just write this as an example and see if you may be able to find something like this at your house. Okay, you've got a faucet, and the water will flow out in a tapering stream. And eventually when the stream gets too thin, it turns into drops coming out. So the tapering water stream is actually an example of the continuity equation, because simply because of the law of free fall, the speed of the water is faster the further down you go, and therefore the cross-sectional area has to be smaller. So this example is the flow out of a faucet. So you may be able to set one of these up and inspect it yourself, okay? Another example, and I think we have a homework problem for this one, is if we have a syringe, so a very thin needle, okay, and some kind of plunger here. There's our picture. Then, we could have pressure here and a very thin, rapid stream coming out there. So we'll see about the homework. We'll have one that's related to this on the homework as well. So yeah, this was the continuity equation, and it just reflects the fact that the mass is conserved. In the more general form, you would have different densities here as well, but we struck the density from both sides, talking about an incompressible fluid. Okay, that would be our fluid static, the first equation of our fluid dynamics. Now for the second important equation, I want to do a demonstration first, for which I brought a shop blower and okay. I had to show you that at length because there's a couple features there. I had an airflow at this angle. Well, let me bring my prop out again. I had an airflow at an angle because had it just been vertically underneath, you might have not been as impressed, okay? But the point that I was making is it was here at an angle and it was not falling down, okay? In fact, how about I do a little repetition of this? Hold on. While the getting is good. that time I made my point. I wanted to demonstrate a couple aspects of that, in particular the fact that the ball was rolling while it was suspended here. Okay, so that's called the Bernoulli effect. It's going to take us a little bit of extra time to deal with. So first we'll just do a picture of this demonstration and bring out the important points. So this is just the demonstration with the beach ball and the leaf blower. It's not a leaf blower, but that's what we used to use, okay. So we have an air stream here coming out, and I'll indicate that it's tilted, okay. And we're suspending a ball clearly not directly over the wind source. So yeah, we can even, good luck. Put some color on this thing. There you go. Now, point that I wanted to show, and it can work better with a better beach ball, but when you do this, the rotation is clockwise, okay? If the air source is over here, the rotation is clockwise. I could flip it the other direction and the rotation would be the other direction. So the rotation works best when you have a beach ball with little ridges on it, which we don't have right now. Okay, you guys get a better one, you can do the same demonstration. But the fact that the air supply is over here, so I'll just call this wind right there, means we have some questions to answer here. Because after all, this ball has weight, mg, and the question now is, why isn't it just falling to the ground? Now, if you're thinking buoyancy, that's actually not 100% wrong. Obviously, that same ball, I have a littler one here, if you just drop it, right, it's not buoyant in the air. Both of these things just fall. However, we can say that the pressure must be greater on the bottom than it is on the top. So the force holding it up would be pressure greater at the bottom than on the top. Okay, so greater pressure down here and lower pressure up here. On the other hand, the direction of rotation tells us that the air speed is greater on top. Okay. So the airflow speed is greater where the pressure is lower, okay, and vice versa. So that's why this thing is actually being held up. And what we have to do is, this is kind of a guess at this point, we have to justify this through the physics, okay? And that'll be Bernoullis equation. So yeah, this is the Bernoulli effect. There are a number of them. Let's just call this a Bernoulli effect. Okay. And I'm gonna just write down Bernoulli's equation. And I'll either refer you to the book for the derivation, or we'll do the derivation later. We'll see how much time we have. Bernoulli's equation states the following. So for 1 and 2, these are just, well, let's not call them balls here. For region 1 and region 2, connected by laminar flow. Okay. connected by a laminar flow. So here's the important equation here. We have P1 plus 1/2 rho V1 squared plus rho G Y sub 1 equals P2 plus 1/2 P2 squared plus rho G Y sub 2. This looks like an energy conservation expression, and in fact that's what it is. It's a work kinetic energy expression. So it's actually pretty easily dealt with. Actually, it's a work mechanical energy expression. If you take the P1 minus P2 on the left side and everything else on the right side, then pressure times volume will equal the change in the energy on the right side. So yeah, that would be the derivation of this. It's not hard to get, but this has some really interesting consequences. So Bernoullis equation for regions 1 and 2, I already said about the laminar flow. And these are the pressures. I'll get us another picture here in a moment. But these are the pressures, the speeds, and the vertical elevations in those two regions. I'm going to go ahead and erase this picture and get a slightly different one going. And then we'll do an application. So the idea is we have a flow. Here's a y-axis with gravity up and down. And we have a flow, a laminar flow. Okay. So we'll call this the region 1, and this region 2. Okay. So they're separated by the y-axis vertically, and there are different pressures and different speeds. Okay. So once again, P sub 1, pressure down here, half rho V sub 1 squared, that's the speed down there, rho G Y sub 1, that's the elevation. I could even, say we've got a Y sub 1 and a Y sub 2, okay. So the sum of these quantities is equal between 1 and 2. So when we do a Bernoullis equation problem, we set it up like an energy problem that we learned in the past. So the simplest example of Bernoullis equation is going to be when y sub 1 equals y sub 2. So let's do that as our first example. Y sub 1 equals y sub 2. And then I'm going to have P sub 1 plus 1/2 rho V1 squared, P sub 2 plus 1/2 rho V2 squared. Now this is worth pondering. So it's on the level, it's not an uphill situation, and you can see clearly if pressure's lower, speed's going to be higher. Okay, so if the pressure's smaller, pressure plus speed squared, then if the pressure's lower here, then on the right side, then the speed's going to be higher. Okay. So note higher speed implies a lower pressure. This is something that is counterintuitive, but I have a good example of it. And this is a demonstration you guys can do anywhere you have 2 sheets of paper. Okay. So you've got 2 sheets of paper, and you just hang them here. Okay, you just hold them here. If I blow between them, you'll see what happens. They come together once again. Let's do this right. So what you saw is when I blow through the pages, they come towards each other. That means the outside pressure is greater than the pressure in the air current itself. Okay, so a very important result. Good. So now I'll just do a couple of more examples with this. This was the simple one that really shows what's going on there. The next example and then I'll assign a couple of problems. Example 2. There's also a problem, I think, in the homework. Suppose you have a big open tank. You know, it's a big open tank on stilts. It's got water inside, and you shoot a hole in the tank. Okay. Shoot a hole here, a small hole, and then water comes out. The question is, what's the speed of the water that's coming out of that tank there? So yeah, let's make sure we've got this thing labeled. So this is our water tank, and the depth of the water is H. So we'll just say it's an open tank. We're just saying it's an open tank, so we say we have atmospheric pressure on top. Okay, so P equals P atmosphere. Okay, and this will be our point 1. Now, where the water is emerging is our point 2, but the water is streaming into an atmospheric pressure itself, so down here we also have atmospheric pressure. Okay, so let's go ahead and write down Bernoullis' equation in 2 steps. So we will have P1 plus 1/2 rho V1 squared, rho G Y sub 1, P2, 1/2 rho V2 squared, rho G Y sub 2. Okay. Just like we did with energy, we just write the thing down. Now we know that P1 and P2 are both the atmospheric pressure. Because atmospheric pressure on top of the tank and atmospheric pressure out where the water is emerging, and I'll just indicate some streamlines. Okay. So those two are actually going to drop from the equation. And now, because V sub 1 is actually the speed with which the water level is dropping, it's negligible, because this is a tiny hole, this is a big tank. So this is approximately 0. And then we've got rho G Y sub 1. And then we have 1/2 rho V2 squared plus rho G Y sub 2. Okay, so this is going to give an interesting unanticipated result. So we're striking the atmospheric pressure from both sides. We're going to solve for V sub 2. Okay, this is just a couple steps, I'll do them right now. We're going to solve for V sub 2. You see we have density that can cancel from each remaining expression. And what we're going to get is, so I'm just going to call this thing star. Star, we get V sub 2 is equal to root 2G, and it'll be Y sub 1 minus Y sub 2. But that is just H. So I'm not even going to write that down now. Root 2GH. So make sure you see these steps. This expression, of course, we've seen many, many times. It's the same speed that something would have that falls through this vertical distance, but nothing's falling right now. There's just the pressure on top, and it's forcing the water out the bottom with the greater pressure down below. Okay. The other thing I could point out is Bernoullis equation without the speeds, it just gives us back the pressure depth formula. So that's interesting in itself as well. It contains the pressure depth formula if you just have speeds being 0. Okay, good. I think I'm going to leave it at that and assign a couple homework problems. Yeah, let's see what we have for the homework. So we're in chapter 9. I'm going to run through a couple problems here. So homework number 34. Homework 34. Chapter 9. Let's see. Problem 32. 32 is a very basic continuity equation problem. Then I wrote down here 37. "37 is that hypodermic syringe I drew on the board earlier. That's the hypodermic syringe, and you'll have to decide whether it's going to be the continuity equation or Bernoullis equation or both, okay? But it's a nice basic problem. Then I have 43, and 43 is basically this problem that I've just talked about here, with an added application to it. But if you understand this one and you understand projectile motion, then you'll be fine, okay? And finally, 47 I should say a little bit more about. 47 is the geyser problem. So the idea is that we have the ground level, and there's a geyser, Old Faithful, over in Yellowstone, that shoots water up in the air, right? And what they're saying is the geyser is a tube connected to some big cavern underground. Okay, so this is ground level. And given the height, you can estimate or you can calculate the speed with which the water emerges from the ground. And based on that, you can figure out the pressure down here in the cavern, okay? So that's problem 47, very nice problem, and that's a Bernoullis equation problem as well. So you have all 4 of these, you'll be in great shape. Okay, good, see you guys next time.